Hi, we built a predictive model that looks at flooding in the city of Calgary and predicts the likelihood of flooding in Colorado Springs. The goal of our project is to create a model that will predict the probability that some defined area of a city will be inundated by flooding. It's vitally important that planners have as accurate a measure of flood risks as possible for a whole host of purposes that include land use designation, resource allocation, and resilience planning for future weather events. Our analysis followed a very specific path. We began by collecting publicly available data on each city, manipulating that data to put in a form suitable for a model, inputting that engineered data into the model, measuring and validating the accuracy, and finally putting it in a legible form that tells the story. This approach of building a model is distinct from the more typical flood modeling analyses that analyze very specific attributes of a given area and often do not take into account a whole range of contextual features that are relevant for determining flood risks. So we created 8 main categories of data, or features, that would become the inputs of our flood model. Basin refers to the watershed, which is the area where bodies of water like rivers and streams flow to. Low elevation points, steep slopes, the distance from streams to steep slopes, the permeability of the surfaces, and land use districts like residential, commercial, and industrial. I'll now briefly take you through an example of how we manipulated or engineered one of our most statistically significant features, in this case, distance to steep slope. First, we downloaded digital elevation data and streams in ArcMap. We then clipped this data to conform to the boundaries of our given city and used the slope function to calculate slope. Next, we reclassified this slope to find the distance from steep slopes to streams. And finally, we created a grid of rectangular cells known as a fishnet to analyze the proximity to steep slopes within each cell. We made this fishnet 500 by 500 meters.
The above maps show the predicted flood values for the city of Calgary and Colorado Springs. The flood in Calgary is in and around the river that flows through the city, while in Colorado Springs, as there is no river that flows through the city, only some cells get designated as flooded. In Colorado Springs, features like distance to steep slopes and low-lying areas become very important. The image on this slide shows the confusion matrix. To read this, look at the prediction and reference column. For example, 1029 fishnets, which were predicted as 0, were actually 0, also called the true negative or the specificity. Similarly, only 12 fishnets were predicted as 1 when the actual value was 1, also called the true positive or the sensitivity. Similarly, you can read the false positive and false negative rates in a similar fashion. The image on the left shows the probability of the event of flood and no flood. In case of flood, the hump of the curve should be over the 1 on the x-axis, while the hump of the no flood should be clustered around 0. The model does not do well predicting flood events. The image on the left shows the ROC curve for the model, which means the possible thresholds for the positive and negative rate. This curve is used to define optimal value to minimize false positives while maximizing positive rates. As we see and we have learned what the data does, the next steps that we think about is that the Calgary model has a poor sensitivity, and we can go back and add more features or do better feature engineering to improve the model. We can also add more features that are present in both Colorado and Calgary and hope the model does better. We can vary the unit of analysis, that is the fishnet size, which we now have it at 500 meters by 500 meters to depict the block size, but the risk of flood could be higher or larger. Thank you so much for listening to us today. Thank you.